Let's build a model for the motion of an object moving through some material. And so let's say it's a slow moving object moving through air in one dimension. So it can't move up or down. It can only move in one dimension. And we'll call this the x direction. And that's the y direction, doesn't matter, but it can only move in the x direction. So it could be a ball moving through the air. I don't really know, but and we're going to make it in 2 dimensions later, but let's start in 1 dimension just to make things easier. So if you put your hand out the car window as it's moving, you can feel that the faster the car moves, the more air is pushing on your hand. That's just drag force. So it definitely depends on the velocity. There's 2 things it could depend on. We can write it like this. F air, or drag, is negative b v. So there's a term that depends on the velocity, linear velocity, and then we could write this, negative c v squared v hat. So this is a term that depends on the square of the velocity. So we're going to assume that we only have this term that depends on the velocity, and that's what's called linear drag. It depends on the velocity to the first power. So we'll deal with this later. So we're just going to have just linear drag. And so with a sphere of diameter d in air, then we can say b, this parameter, is equal to beta times d. That's a d, that's not a b. Where beta for air is going to be equal to 1.6 times 10 to the negative 4th Newton seconds per meter squared. Which doesn't really matter right now, but we're going to use that. We're going to do some numbers later. Okay, so let's just say it starts with some initial velocity v0, and then we can write Newton's second law like this. F net equals ma, the acceleration, and that's going to be equal to negative b times the velocity vector v. We can smash this down into 1 dimension, right? Because nothing happens. The acceleration is only in the x direction. The velocity is only in the x direction. So I could write this as I'm using the scalar values for a and v. They are x components really though. Negative b v. So there's my Newton's second law. And now I can write the acceleration as dv dt. That's the derivative of the velocity with respect to time is the acceleration. And I divide both sides by the mass. I get negative b over mv. So that's my differential equation that I want to solve. So in this case, we can treat the terms dt and dv as separate variables. And so if I can get all the velocity terms on one side and all the time terms on the other side, then I can do something. Okay, so you can't always do this, but in this case, I can. Because think about what's happening here. This is a time derivative of velocity, but then it depends on the velocity. So it's not just straightforward. You can't just integrate both sides like it is. I need to get this v on this side and the dt on the other side. So let's multiply both sides by dt. I get dv equals negative b over m v dt. And now I can divide both sides by v, and I get dv over v is negative b over m dt. With this, I can integrate both sides because this side only depends on v, that side only depends on t. So if I integrate both sides, I'm doing the same thing to both sides, it's fine. And I'm going to do an indefinite integral, which means that when I integrate, I'll have a constant in their term too. So here I have the dv over v. So this is like v to the negative 1. You know, you can't do the power rule here because if I add 1 to the power, I get v to the 0. It doesn't, then divide by 0, it doesn't work. So the derivative, the integral of dv over v is just going to be the natural log of v. So you can look that up in your integral tables. So it's going to be the natural log of v for this side. And then over here, I have negative b over m. That's just a constant. And then dt. So I just have negative b over m. I integrate dt, I just get t. And then I have a constant. Now, at t equals 0, the velocity at 0 is going to be v0. So let's put in t equals 0 and solve for the constant. So I have the natural log of v, which is I'm using v0, right? Because that's the time, the velocity at t equals 0. And this is going to be negative b over m times 0 plus c. So that means that c is going to be equal to the natural log of v0. So if I put that in over here, I get the natural log of v equals negative b over m t plus ln of v0. And that's really nice because really we don't like this. I don't like the natural log of something with units because that you can take the natural log of a number, that's for sure. But what do you do with the units? And it doesn't really work. I mean, it's cheating. It's rude. It's just bad form. It's just barbaric, and you shouldn't do it. But if I subtract the natural log of v0 from both sides, then I get a difference in natural logs, which is the same as the ratio of v over v0. So I can write this as ln of v over v0 equals negative b over mt. Now what I want velocity as a function of time. So let's just take both sides of that, raise it to the power of e. So I'll write that as, here's what we had, natural log of v over v0 is negative b over mt. So if I raise each side to the power e to that power, I get e to the natural log of v over v0 is just v over v0. So v over v0, and this side I get e to the negative bt over m. Now I'll multiply both sides by v0, and I get v as a function of time is v0 e to the negative bt over m. So what does this say? This says that at time t equals 0, if I put t equals 0, it starts at some velocity v0, because this is just 1. That makes sense. As t gets greater, this is e to the negative number, so it's going to get smaller and smaller. So this says that as time goes on, the velocity is going to get smaller and smaller. So if I graph that, it should look like this. V as a function of time versus time starts at v0, and then it would just exponentially decay down like that. Okay. Now, but what about the position as a function of time? So if I want to find position, I'm going to write the velocity as dx dt equals v0 e to the negative bt over m. And again, I can separate variables. I actually don't have any x terms over here, so it's pretty easy. I can just multiply both sides by dt, and I get dx equals v0 e to the negative bt over m dt. Now I can integrate both sides again. So this is pretty easy. The integral of dx is just going to be x. And then over here I get the integral of this. Okay, so I have v0, and then I integrate e to the negative bt over m is e to the negative bt over m. But then I have to divide by the derivative of this stuff, right, to get that to work. So that's going to be negative v0 m over b, and then I get e to the negative bt over m, and then I have to add a constant c because it's indefinite. And just so you know, I mean, I wasn't clear before. These are both indefinite integrals, but I only need one constant, right? If I put a constant here and a constant there after the integrating, then I can just add them together. So I only need one constant. So again, let's say at t equals 0, x of 0 equals x0. So let's put in t equals 0. So if I have at t equals 0, I get x0, negative v0 m over b, e to the 0, right, because I put in t equals 0, plus c. So this is just 1. So this means that c is going to be x0 plus this term, right, because I have that times, I have to add that to both sides, plus v0 m over b. So if I put that in up here to my function, I get x as a function of t. It's going to be equal to this term. Let's just put that. It's negative v0 m over b, e to the negative bt over m, and then plus c, which is going to be plus v0 m over b plus x0. And so here I have Both of these have the same term in there, so I can factor that out. I get x0. Let's write it as plus v0 m over b times 1 minus e to the negative b t over m. And that's, okay, that's x. I saw this. That's x as a function of t. So what does this say is going to happen? Well, let's start again. Let's double check. At t equals 0, this term is 1. So I have 1 minus 1 is 0. So I just get x0. And then as t gets larger and larger, this term is going to be smaller and smaller. And so I'm going to end up with x0 plus this thing. So let's just say I start at x equals 0 and I make a graph. Here's x as a function of time. It's going to start here at x equals 0, and then it's going to approach this term, which is v0 m over b, like this. Pretty cool, huh? Okay. I'm going to do two things. Number one, I have these two functions. I'm just going to plot them. I'm going to plot them in Python. Okay. In order to do that, I do need some parameters. I already have the value for beta, right? So I have, let's just put it right here. I need v0, m, and b. So did I say what b was? Yeah. Okay. Let's put it right here. So I have beta. I need m. So let's do this. Let's say it's a drop of water where d is equal to 0.2 millimeters, 10 to the negative third meters. And the density of water is 1,000 kilograms per cubic meter. So with that, I can calculate b, right? Because I can calculate the mass from the diameter, knowing that the volume of a sphere is 4/3 pi r cubed. So I can get that. I can get b. I can get all my parameters. I just need one thing, v0. Let's just pick v0 equals 0.5 meters per second. Okay, so I'm going to graph that in Python. I'm going to make those two graphs. So let's do that, and then we'll come back, and then we'll do this same problem another way. So we get to do it twice, and I know that's very exciting. Okay, so let's jump over here to Python. Okay, so I am using GlowScript vPython. If you're not familiar with plotting in GlowScript vPython, just let me know. I do have some tutorials on this, and I can give them to you later. But I'm just going to jump right in. If you haven't done this before, it shouldn't be too bad. I'm going to make a nice, pretty graph. You don't have to make pretty graphs, but I am. So to make a pretty graph, the first thing to do is to make the axis for the graph. So I'm going to say I need to give it a name. G1 equals graph. I'm going to give it a title. No. Yes. Title equals, let's just call it velocity. Should I say linear drag? Linear drag velocity. How about that? And then I need to give an x title. X title, you don't have to, but I am. Title equals x in meters. No, time in seconds. And then I'm going to give it a y title. V, meters per second. And then I'm going to give it a width. You don't have to do that. I am doing that. And a height. I'm going to make it skinny. Height equals 200. And then you'll see why. Okay, so now that just makes the graph. Then nothing would really happen if I run that. It might show something. No. I need to plot something in there. So I'm going to say FV. Let's call it FV. Is G curve. Color equals color.blue, and then I'm going to say graph equals G1. So this is important because if you have more than one graph, more than one set of axes, which I'm going to have, I need to tell which axes to plot this in. Okay. So should I just make the velocity? No, let's just make both of them. Now let's make the other graph. G2 equals G graph. Graph is a built-in function in GlowScript vPython. Okay, so it's already there. Title equals linear drag position. X title equals time. I should have done this all beforehand, but that's fine. Y title, and I'm going to give you the code. Okay, equals x in meters, and then width equals 500, height equals 200. And then fx equals g curve. Let's make it blue also. Color equals color.blue. Graph equals g2. Okay, so now I'm going to go ahead and put my parameters. I know the diameter is 0.2 times 10 to the negative 3. I know rho is 1,000. I know beta is 1.6 times 10 to the negative 4th. Is that right? And then V0. Let's say V0 equals 0.5. Okay, so I need to find the mass. I need to find B, the mass in B. Okay, so let's find the mass. I'm going to say RR equals D over 2. I like to think in terms of radius. So then M is going to be the mass, which is the density times the volume. So it's going to be rho times the volume, which is going to be 4/3 times pi times r cubed. That's the volume of a sphere, 4/3 pi r cubed. And then B is beta times D. That's what I said, right? Yeah, so it's just going to be beta times D. Okay, so I have that. The other thing I have my initial velocity. I need my initial x position, x0 equals 0. Okay, and then I need t equals 0. And what I'm going to do is just move forward a certain step in time, calculate v, calculate x, and plot it. So I need to know how much I step forward each time. If you use other plotting programs, they'll just do all this for you automatically. But I really think it's useful to do it manually. I think it helps you understand everything that's really going on in there. So let's just pick 0.01. And now what I'm going to do is I'm going to plot. I'm just going to pick a time. Let's say 3 seconds. Okay, I'm going to run it for 3 seconds. We can change it if we need to. So I'm going to say while t is less than 3, do the following. Did I save this? No. I didn't give it a name either. Linear drag plot. Save. How can I give you the code if I don't save the code, right? Okay, so while t is less than 3, the first thing I'm going to do is to calculate x. I know my equation for x. I'm looking at my equation for x right here. I'm going to just go ahead and say x equals x0 plus v0 times m divided by b. I'm going to put that in parentheses just so it looks the way I like it to look. Times 1 minus exponent, which is exp, and then everything raised to that. Negative b times t divided by m. That's it. And then v is going to be equal to v0 times exponent negative b times t over m. So I have both of those things calculated. I just need to plot them. Fv dot plot tv, fx dot plot tx. Now I do need to increase time, right? Because once I've done that, if I don't increase the time value, then this loop will run forever, and that would just be awkward. So t equals t plus dt. This should run, but there could be an error because you never know. It's real life. Okay, so the first thing I did, I'll let it run too long. Let's let it run for half a second, and then it'll look a little bit better. That's not too bad. Let's let it run for 1 second. Okay, I'm pretty happy. That you see the two graphs, and they're right next to each other. They have the same time, and that's just a pretty thing. I can't plot both of those on the same graph. I mean, you could, but one, the values are much different. It didn't go very far, and so you would, the axis wouldn't really make sense, and they wouldn't be scaled correctly. So it'd be better just make two graphs. So that's that. Two graphs. Pretty happy. Okay, what I'm going to do is to make two more graphs. I'm going to again plot the position versus velocity, but I'm going to do it a different way and see that we get the same thing. So let's go back over here to the code. Let me go switch to the paper and show you we're going to do a numerical calculation using the Euler method to do the same thing. Okay, switch back to paper. So let's go over here. And I'm going to actually do this as a vector problem because I like vectors, and this will be better for later when we switch to two-dimensional motion. So here's my ball, and it has some velocity. So the velocity is that way. The velocity vector, and this is F drag. I'll call it FD. So I can write this. F net equals MA. We did that before. And that's going to be equal to negative B times V. We already said that. So if I solve this for the acceleration, I get A equals negative B over MV. So here's the deal. I can calculate the acceleration for this object. But suppose I break this into delta t equals 0.01 seconds. And I break this into a small time step. During that small time step, I can assume that this force, this acceleration is constant. I'll assume the acceleration is constant. It's not. Okay, but over just 0.01 second, it's kind of constant. So if I do that, I can say A, which I just calculated, is delta V over delta T. It's a change in velocity. So here's my velocity V1, and then a little bit later, here's my velocity V2. So this is going to be equal to V2 minus V1 over delta T. Assuming A is constant. A approximately constant. And it's a vector, right? Because you can't have a vector equal to a scalar. So if I solve this for V2, I can multiply both sides by delta T and add V1. I get V2 equals V1 plus A delta T. So I just calculated A with my initial velocity. That's technically V1. And then I use that to find the new velocity. And this is wrong, but it's only kind of wrong. And only kind of wrong means kind of right. So that's cool and everything. But now I can do the same thing. What if I assume this velocity is constant, which you're thinking that's just crazy, but let's do it anyway. So let's say V is approximately equal to a constant, which I just calculated, so why would you do that? Just hear me out. So I can say, let's say this has a position R1, and then it goes to some new position R2. So I can say V equals V2 is delta R over delta T. That's a definition of velocity. It's the change in position with respect to time. And I'm using the second velocity because I just calculated that. And so again, I can say that's R2 minus R1 over delta T. That's a delta. So I can solve this for R2, and I get R2 equals R1 plus V2 delta T. So that's my Euler method calculation right there. I'm going to start with some initial position and velocity. And so I need to know those. And then I'm going to calculate the velocity, or I know the velocity. I can calculate the acceleration, use that to update the velocity, use that to update the position, and then do it all over, change time, and go back up here. Now I have a new velocity, so I have a new acceleration. So I have to do this again for V3 using V2, and then R3, and then just keep doing that over and over again. And so that's a pain, but computers can do it and they don't mind. We're going to do this as a vector equation in Python because that's what shows how powerful ClosedScript VPython is. And then when we do this in 2 dimensions, which yes, we will in another video, it will make more sense. So let's jump back over to Python and put this stuff in. Okay, so here I am in Python. I'm going to need 2 more graphs, and I'm going to need 2 more variables. So let's go up here and just add the graphs in first. So I'm going to say FV2 is G-curve color equals color.red, just so we can tell them apart. Graph equals G1. And then down here, FX2 equals G-curve color equals color.red again, and then graph equals G2. Now, I also need to put in an initial velocity and position vector. So down here, let's just do it here. Let's call it, I did use v. So let's say vv for vector velocity. And that's going to be equal to, it's moving in the x direction, but I'm still going to write it as a vector. So I'm going to say this is equal to the vector v0, 0, 0. And then we can change these things up, and we can see what happens, but right now let's just do it this way. Now I need an initial position. I can call this just r. And that's why up here I called that r, because I'm going to use r for position. It's going to be the vector x0, 0, 0. That's all I really need. So down here, what I'm going to do, I've already done my theoretical calculation. The first thing I'm going to need to do is to calculate the acceleration. I don't have it up here, so I can do that. A equals negative b times vv over m. So I'm using vv because that's my vector velocity, right? I can't use v because that's a scalar value right there. So that's my acceleration. I calculate that every time I go through this step. I do that. Now I can use that to update the velocity. vv equals vv plus a times dt. So this is really cool because number one, this is a vector update equation. This is a vector equation. This changes both the x coordinates, the y coordinates, and the z coordinates because vv is a vector, a is a vector. So this is a vector equation. Python can handle that. Now I'm going to update the position. R equals r plus vv times dt. Now I just updated the velocity, so this is technically velocity 2. Velocity is the end of the velocity, and again, it's a vector equation. So that's it. I've already updated time. I just want to plot these things. So let's go down here. fv2 dot plot t. I can't plot vv. vv is a vector. I can't plot that. I can plot the x component of that. So that's going to be vv dot x. And then same for the position. fx2 dot plot t r dot x. That's it. I should save it, and then I should run it. Okay, they're not the same, right? They're not the same, but they're pretty darn close. This only runs for, the important stuff right here happens in 0.2 seconds. And so I only have 20 calculations, but if I'm using a time step of 0.01. So one thing I can do, my approximation that the velocity is constant isn't really good for that small of a time, that large of a time step. So let's just change that. This is pretty easy to do. I'm going to go down here and just make the time step 10 times smaller. And now you can't even tell that there's two graphs. They're right on top of each other, right on top of each other. And I think that's kind of awesome. Now we can go over here. We could change the velocity. What would happen if I have a negative velocity? It should still work. Let's try it. Okay, so now it looks the same. It's just everything's in the negative direction. That's fine. I could give it a larger velocity. Let's say something crazy like 1.5, and it still looks fine. So there you go. That is. I should check. Look, this is. The final velocity, the final position is, what's that? 0.875. Let's just print that out. I said what it would be. Oops. So let's say print. What's it in the equation? It's v0 m over b. So v0 m over b equals v0 times m divided by b in meters. And let's just see if we get something like the same thing. So oh no, that is right. I'm sorry, I was reading the x value. Yeah, so this says 0.195, 0.196. It's pretty good. Okay, so that is the asymptotic position right here. The velocity is 0. That's easy to do. Okay, so that's motion with linear drag in one dimension. Code down below. This is part of my classical mechanics class. I'll put the playlist for that down below too. If you have any graphing questions, if you have any Python questions, just let me know in the comments. I'll be happy to help. I'm going to do two-dimensional linear drag next, projectile motion with linear drag. It's going to be fun. It's going to be based on this, but I'll go over the same stuff again. So hopefully that helps. I'm leaving.